acids. They're found in all branches of life. They're often very biologically active. So this is an example of a cyclic peptide that comes from a plant. And you can see it's about 20 amino acids in a ring, and it has very unusual three-dimensional structure, including multiple disulfide bonds that fold it up and keep it in this rigid shape. Cyclic peptides have many interesting properties. They're very stable to extremes of pH and heat. They're resistant to proteases. They have enhanced membrane permeability compared to linear peptides. And they're rigid. That means that they can bind much more actively to a site than a floppy, flexible linear peptide. There's two ways to make small peptides, either on ribosomes, and these are called RIPs, for ribosome-encoded post-translationally modified peptides, or non-ribosomal by enzymes called non-ribosomal peptide synthetases. And this is how I got started in cyclic peptides, and I'm going to tell you that story very briefly. Well, I mentioned that cyclic peptides come from all over. Bacteria, venoms from spiders and snakes, cone snails make venoms that they use to attack other snails, and plants make many kinds of cyclic peptides. But until our work, it was not known that any ribosomally encoded, ribosomally synthesized peptides were made in fungi of any sort. Here's a small example of many kinds of cyclic peptides that we know about, from important drugs like cyclosporin, toxins, of course, like alpha-mannitine, some important drugs like ergotamine also, and then compounds made by plant pathogenic fungi such as HC toxin that I've spent a lot of my career studying, Victorin. The precursor to penicillin is also actually non-ribosomal peptide. But this one is one I've spent many years studying. It's a cyclic tetrapeptide, 4 amino acids. Notice it has D-alanine and D-proline as well as L-alanine. It has this fourth unusual amino acid. And this is a critical virulence determinant for this particular fungus called Cochlealis carbonum, which is an ascomycete. Maize plants that are susceptible, maize plants that are sensitive to this compound, because the fungus makes it, it's highly virulent. It kills the corn completely. And these plants differ by a single resistance gene, and they're completely resistant to this compound. So we did work on the basis of resistance, which is actually an enzyme that degrades that. This is my fancy slide. The resistant corn is resistant because it can degrade this toxin, inactivate it. And if it can't do that, then this toxin inhibits an enzyme called histone deacetylase. And somehow, that gives this extreme susceptibility. So one of the things we did was identify the genes that make this compound in the fungus Cochlealis carbonum. So the enzyme, the non-ribosomal peptide synthetase that makes this enzyme, has several key characteristics. One, it's very, very large. 5,200 amino acids. A single polypeptide, shown, the entire sequence is shown here. These non-ribosomal peptide synthetases have a very strong modular structure. So there's one module for each amino acid shown in purple. So this module activates proline. This module activates alanine. This module activates D-alanine, and this module activates the fourth amino acid, ADO. There's another module here that's the pimerase. This converts L-proline to D-proline. Now, before our work in the Amanita toxins, all peptides from fungi were thought to be made by enzymes like this. And so when we went looking for the Amanita biosynthetic genes, our working assumption for many years was that it would be an NRPS. Now there's several ways now that we have many, many NRPS genes cloned, sequenced, is that you can, for example, design PCR primers against conserved motifs in each of these domains. So it's not shown here, but there are certain amino acid motifs that are conserved between all 4 domains. and you can do PCR to identify a new NRPS. So that's one approach. The other one is that these would be very large, and so once we found it, we'd expect, if you wanted to make something like amanitin, which has 8 amino acids, you would expect to find an enzyme with 8 domains, not just 4, but 8. So we worked on this assumption for many years, for a long time, a lot of PCR reactions, and we never ever were able to identify any genes out of amanitin. This work started partly because of my background working on cyclic peptides for filamentous fungi, but partly because I was on the thesis committee of Heather Hammond, who was a mycologist down the hall in the same building, who was working on Amanita systematics and taxonomy. And as we started to talk, we realized that nobody had identified the genes for alpha-amanitin biosynthesis, and that it seemed like a logical collaboration between me and her. But I knew about the molecular biology and the biochemistry, but she knew about the mushrooms. Very important, because it took me a long time to be able to identify and define these mushrooms, and I'm still not very good at it, but I know a lot more than I used to. This is Heather collecting actually a species of canosity that grows in the lawns at Michigan State University. You probably recognize the children's garden, right? Collecting mushrooms, but here she is in the woods doing the taxonomy, collecting mushrooms. This is Amanita bisporidula that grows in Michigan. This is an alpha-amanitin producing fungus that's native to Michigan, pure white Amanita. So she spent several years on and off doing other things as well, trying to look for the genes that were finally, with all of our PCR reactions, working on the assumption that it was an NRPS, everything failed. And we did a lot of other kinds of approaches as well, feeding studies with radiolabeled amino acids, et cetera. But what finally gave the breakthrough was the genome sequencing of this mushroom. And the genome sequence gave us the genes, as I'll tell you in a minute. So first, a little bit about the toxins that are made by Amanita mushrooms, which I'm sure is familiar to many people here. Alpha-amanitin is a bicyclic octopeptide. It has 8 amino acids in their ring, and then a cross bridge between tryptophan and cysteine to form this cross bridge here. In addition to 8 amino acids, there are several hydroxylations, there, modifications. This is why the Amanita mushrooms are so toxic, is due to alpha-amanitin and related molecules like beta-amanitin, which differs by a single amino acid. And the reason they're so toxic, as you know, is because it's a strong inhibitor of this enzyme called RNA polymerase II, which is responsible for making all of the messenger RNA in neuronal cells. So the DNA comes in, DNA goes out, and a single-strand messenger RNA copy shown in red is made, which then is translated into protein. So if you don't have this enzyme, or if this enzyme is inhibited, then the cell's gone. The co-crystal structures in salts are known very precisely where alpha-amanitin fits into that enzyme. Now again, as I'm sure you all know, Amanita mushrooms are also notorious for making phthalate toxins. You know this? You were all right? Any translation?
I'll ask.
Okay.